So in this lecture, we will introduce the basic concept of what are called the fluid antenna systems, FAS systems. For very high data rates in 6G communications, it has been proposed that we'll use extra large multiple input, multiple output systems. So what happens in an MIMO or multiple input, multiple output systems, that we have multiple antennas at transmitters and receivers. What this makes is that it creates multiple paths between the transmitter and the receiver. It's not only one antenna and one antenna at transmitter and one antenna at receiver. There are multiple antennas at the transmitter and multiple antennas at the receiver, and therefore multiple paths are created to avoid multipath fading. We can use different data to be transmitted on multiple paths that will increase the capacity, and this is known as a spatial multiplexing. Or what we can do, that when the channel conditions are adverse, we can send the same data on multiple links, and that will enhance the reliability of the system and thus giving us spatial diversity. So in MIMO systems, we basically have a transmitter that has suppose n antennas and a receiver that has m antennas, and therefore the channel is an n cross m matrix, and therefore the order of MIMO systems just decides how many multiple paths can be created between the transmitter and the receiver. What are the advantages of MIMO systems? Historically, increased channel capacity due to transmission of multiple data uh, across multiple paths, improved spatial efficiency because we can now be transmitting more number of bits per hertz, enhanced link reliability as per the diversity gain, and interference mitigation through beam forming. We can change the antenna directions, and energy efficiency also increases. Robustness against the multipath fading is one of the key uh, advantages of the MIMO systems. The compatibility and scalability, we can increase the order of the MIMO systems in order to increase the data rates or increase the reliability of the systems, and enhance physical layer security because we can the intrusion can be avoided by creating multiple paths between the transmitter and the receiver. Now, apart from that, there are several disadvantages, so to say, and the main disadvantage is the one is this, that the hardware complexity and signal processing complexity increases, which means to say if we are talking about the base station, there is no such problem. But when we are talking about the mobile phones are very small, and to integrate a large number of antennas in the mobile hardware will obviously increase the burden on the battery life of the mobile phones and also the weight of the mobile phone, and therefore this the multiple antennas that are required on the transmitter creates a large hardware complexity. Other disadvantages are it will require high power consumption leading to lower battery life. Channel estimation becomes a very big problem. You can see channel estimation uh, details in this channel only. I have recorded uh, the proper definition of and how channel estimation is done in wireless communication systems. There is one another major disadvantage, that is of correlated fading. I will show that in the next slide. And the implementation cost is also it is more expensive, and it's more bulky, it's more expensive. So MIMO systems have the advantages of spatial multiplexing and diversity, but they suffer from these disadvantages also. And the spatial correlation is a very big factor, which means to say that uh, MIMO uses signals at antennas undergoing independent fading. So it means that the multiple paths which are created, suppose n cross m paths are created, then all of them are undergoing independent fading. They cannot be dependent, and for that we need the correlation between the two paths to be zero. For that, the J correlation coefficient, this Bessel's function J naught of 2 pi d upon lambda, where d is the Fraunhofer distance, is made to be zero, and this gives rise to approximately making the distance of separation between two antennas to be zero point 0.5 lambda. Lambda is the wavelength at the operating frequency, so which means that lambda is equal to c upon f, right? So this has to be the minimum distance between the two MIMO ports, which means that if there are this separation is not maintained, then the two paths will not be independent. This criteria will not be fulfilled, and therefore they need to be at least, you can see here, at least half wavelength apart. If antennas are too close, they also interact in the near fields, and this couples with the information signal that is to be transmitted. And this lambda by 2 distance restricts the number of antennas in the mobiles. You cannot have multiple. We can say 128 cross 128, 512 cross 512, but in principle, it is not possible. So the solution that has come up recently, it's a very new system, are called fluid antenna systems, where interestingly we have a single antenna that can switch locations instantaneously in a linear space. Now, both these three things, all these three things are very important. There is only one antenna. It can switch locations, and it will switch locations only in linear space. It is possible that locations of the antennas can be changed, and all the possible locations are said to be the ports of the FAS system. FAS stands for Fluid Antenna Systems. The selection diversity is used to switch all ports to the port having the maximum SNR, or you can say the best channel condition. The most favorable channel condition can be received by switching from one port to another port. Multiple antennas without space limitations, because actually there is only one antenna. So the space limitation is that is there in MIMO systems can be avoided. It is proved that an increase in the number of ports increases the reliability. If it is possible to change the locations of the antenna from one location to another, the larger the N, the less is the outage probability. I have discussed outage probability in this channel also. You can see my videos. So it reduces the hardware requirements, because now we do not want multiple antennas. Actually, there is only one antenna that will change its location, and increases the cost efficiency. Because these were the major disadvantages of MIMO systems, which are said to be in principle avoided by fluid antenna systems. So what is the principle of them? The basic principle is that antenna can switch location instantly in a small linear space. I will show in diagram also. How can this be done? So fluid antenna system means there is going to be a fluid. So some metallic components like gallium or gallium indium, these are used as fluids under which the antenna is immersed. We can also use some salts like NaCl and KCl for antennas, and ionized solutions also can be used. So these are the basically fluids parts of it. So we use these fluids, we control these fluids, and the fluids control the location of the antenna among n ports. One antenna in one linear dimension can have n ports. This is the major thing about the FS system, because you have only one antenna, but due to its immersion in the fluid, it can go into n ports. In a space that is very small, we can have an n that is very large. So it can move from one place to another place in a very large number. N can be 200 to 250. In research works it had been reported. So you can understand that kind of basically a spatial multiplexing or a spatial diversity can be done. Mutual coupling is not a problem, as there is only one antenna, which means now the lambda by 2 restriction is not applicable. It's only one antenna. So the antenna doesn't need there are not multiple antennas which need to be lambda by 2 apart. It's only one antenna. So there is no this restriction that the two antennas can be lambda by 2 apart only. So therefore there is no restriction on getting more n, and the port with higher SNR can be selected. So in principle, how it is done? So there is a mobile phone, and in the mobile phone we have this fluid antenna system in which there is an antenna, and there is an antenna. This is the antenna. This here is the antenna. This is the antenna, and this antenna is regulated using the radio chip. So there is a radio chip. The antenna can move from various locations, and the location which it gets gives us our n ports. And of course there is going to be a fluid. So the fluid is here, the fluid is here, and there are this and these points which control the fluid. So this is the fluid control system. So fluid control system controls and this radio chip. So these fluid control systems and radio chips together work to change the location of this single antenna among these ports. So there are now basically n ports. These are n ports which are now available. There is only one antenna, but there are n ports because of its movement in its interaction with the fluid. The fluid is going to be metallic or going to be an ice salt. And the complete distance is defined to be lambda into w. This is the linear space in which the antenna propagates, where lambda is of course the wavelength at the frequency, and w is said to be the linear dimension. So I've written, if there are two ports and we take the first port to be the reference, suppose I take this port to be the reference, I take this port to be the reference, then the separation between any two ports is said to be k minus 1 upon n minus 1 into w lambda, which means if suppose there is going to be a kth port and I take the first port to be the reference, then the difference between any two ports, so if there is suppose kth minus 1 at port is there, so this is my delta, right? So this is defined as k minus 1 upon capital N minus 1 into w into lambda, where this w into lambda is said to be the linear length, and this is how we define. Now, if I talk about its channel model, you can understand that now there are going to be basically multiple ports, n ports. So the kth port, if we talk about a kth port, suppose there is a kth port, so this kth port receives the signal r suffix k, which is hk multiplied by x into nk. What is h? Hk is the small scale fading. So you can model it in using relay fading, Nakagami fading that I have discussed previously in my lectures. And what is this X? X is the information signal, so it can be a BPSK modulated symbol that we want to transmit, and NK is the additive white Gaussian noise component. So we basically can model the kth component like that, but you have to understand this is the kth component. How many total components are possible? The total number of possible components are n. So if I want to rigorously analyze all the received signal at the n ports, various n ports which are available, it's a very complex mathematical computation, and that's where the whole future of this FA system leads to. So it's a very promising future aspect that we can avoid a hardware restriction, a hardware complexity, cost complexity, lambda by 2 restriction of MIMO systems by replacing them using one antenna that is immersed into a fluid, and because of its presence and interaction with the fluid, it can take on one of those n ports, but it needs very careful analysis, right? uh, Major issue with mathematical computation is that the tractability is major issue, which means that you derive the expressions, but the expressions are generally given in integrals. What is the reason? The reason is that if I want to calculate the outage probability, I have previously made various videos on this. So outage probability is basically if I have the CDF, so that CDF computed at a threshold SNR. Yeah? So if it is smaller than that, then what is the probability of that? Yeah? So what is it basically means that what is the probability that the overall SNR is smaller than the threshold SNR. Now for this, we need to compute what is the CDF, and for this we require the joint PDF of the system. So actual computation, what is CDF also? The CDF capital F of X is basically integration 0 to X. F, small f is the PDF, Fy dy. So if we integrate the PDF from 0 to X, we get the CDF of the system. If we put X is equal to X, we replace X by gamma TH, we get the outage probability. This is the reliability of the system. Now, for this case, how many different channels are there? Remember that we discussed that there is going to be the kth received signal is given by this. So all in total, there are n signals, and therefore there are n different HKs. Remember, my now HK belongs to where the K belongs to from 1 to n, right? You can understand this. So with this in mind, we can understand that now if I want to calculate the CDF, it will be joint CDF. So the received signal, suppose they are random variables R1, R2 up to Rn, it requires not only this one integration, but now it requires n-fold integrals, right? It requires n-fold integrals. So if I have individual PDFs given by P, H1, H2, HT, T1, T2, so these are the joint PDFs, right? These are the joint PDF. So I first of all require the joint PDF of all the channels. Generally, while mathematical computation, we will assume that all the HKs are independent, and we will assume that all the PDFs are multiplication of each other. That's a different story. But actually, computation requires that you compute an n-fold integral of the joint PDF where we will have h1 h2 up to hn, so you can understand it's an n-fold integrals. And we talked about n being large, 25, 50, 100, 150, 200, 250. That has been reported in the literature. So therefore, if I want to compute mathematical analysis of the fluid antenna systems, it requires, it still is an initial phase, and a lot of research is attracted towards this. There are various approximations that have already been proposed in various papers, but the mathematical computation is quite complex. So this is a very interesting and a very promising future aspect of fluid antenna systems that will be covered in 6G communications to accommodate the highest data rate that is required. But it requires a large attention of the research community, and therefore I also request my viewers to go into it in details. Thank you for watching this video.